When you use condensation reaction to synthesize heteroaromatic rings, you can divide into two categories. The first type is when you use heteroatoms to form both carbon heteroatom bonds to lead to the ring. This occurs with both 5-membered ring and 6-membered ring. Another type is when you need one C heteroatoms bond formation, and another one is the CC bond formation to form the ring. If we consider the first type of reaction for the formation of 5-membered ring, the key starting material is the 1,4-diketones, where you have two carbonyl groups at position 1 and 4 to each other. These two carbonyl groups can be electrophiles, and if you have a nucleophile such as the heteroatom like amines, this can attack the first carbonyl group to form carbon heteroatom bond, and then you can repeat the attack at the second carbonyl group to form the second carbon heteroatom bond. And now you can see that you have two hydroxy groups that can be eliminated out. For the mechanisms, you can use the lone pair of nitrogen to kick the OH out, so you get iminium first, and from there you can have the base or something to accept the proton here to make it enamines. And this process can be repeated again with these hydroxy groups with the proton here to form the second double bonds, and eventually you are going to get pyrrole as the final product. For the type 1 synthesis of 6-membered ring heteroaromatics, you need to use a different starting material, which is 1,5-dicarbonyl compound, but in the molecule you should already have one carbon-carbon double bond to lead you directly to the aromatic system, and here is why. So if you have a 1,5-dicarbonyl systems which can act as electrophiles, and then you have the heteroatoms like amines acting as a nucleophile, the first attack of amines to carbonyl groups will lead you to the first carbon heteroatom bond, and now the second attack to the second carbonyl groups will lead you to the second carbon heteroatom bond, and now you have two hydroxy groups which can be eliminated out. So you can remove 2 molecules of water if you follow the general mechanisms to form 2 double bonds here. So if your molecule already starts with 1 double bond, now you have a 6-membered ring that has 3 double bonds, which is aromatic, and you are forming an aromatic system which is a pyridine. But if your 1,5-dicarbonyl compound doesn't have a double bond to start with, okay, you can follow the same reaction by using the 2 carbonyl groups as a electrophile, and if you use the heteroatom like amines as a nucleophile, so after attacking twice, you are forming 2 carbon heteroatom bonds with 2 leaving groups here. So you can remove 2 molecules of water here and here to get 2 double bonds, and you can see at the moment in the 6-membered ring you only have 2 double bonds, which is not aromatic yet. You need to introduce 1 more double bonds. So there are a few ways to do this, but the most straightforward way is to oxidize these hydrogen. So oxidize the ring system by removing the 2 hydrogens here. So there are some different types of oxidants that can achieve this, but since the product is so stable, you don't need to use that harsh conditions. Sometimes just air is enough to oxidize to get aromatic ring. For the type 2 synthesis of 5-membered ring, you have many possibilities to synthesize this because there are so many carbon-carbon bonds that you can form. But one of the possible way is to use the beta carbon of enol as a nucleophile to attack the carbonyl group of another molecule, and you are going to form a new carbon-carbon bond, and after that you get the carbonyl group. And if another molecule already have halogen installed, you can use the lone pair of halogen to attack the carbonyl group to form a carbon heteroatom bond. So in total, you form 1 carbon-carbon bond and 1 carbon heteroatom bond. And you can see that now you have 2 hydroxy groups that can be eliminated. So if you follow the same mechanisms, you can remove 2 molecules of water, and at the end introducing 2 double bonds and forming aromatic systems. For example, furan, thiophene, or pyrrole, depending on which heteroatom that you use. For the type 2 synthesis of 6-membered ring, again, there are many possibilities, but one of the possibilities is to use, for example, if you want to synthesize pyridine, you can start from an enamine as a nucleophile to use the carbon to attack 1,3 diketones. So it will attack one of the ketones to form the first carbon-carbon bond, and after that you can use the heteroatoms here as a nucleophile to attack the electrophile as a carbonyl group and forms another carbon heteroatoms bond here. And after that you have 2 leaving groups, this OH and that OH. So by removing 2 water molecules, you will complete the aromatic systems to form pyridine. Another different way is to, sometimes if you have more than 1 heteroatoms in the ring, you can use both heteroatoms as a nucleophile. For example, here you have this nitrogen and that nitrogen, both of them has lone pair. So you can use them as a nucleophile to attack both carbonyl groups. So this one will attack here, this one will attack here, and at the end, after you remove 2 molecules of water, you form pyrimidine. Or for pyrrole, you have 2 nitrogen next to each other, so you can use hydracenes that has 2 amine groups next to each other. So these 2 can attack the carbonyl groups, and then after that the lone pair of this nitrogen attacks here, the lone pair of this nitrogen attacks here. Removal of 2 molecules of water to complete the aromatic system to form pyrrole. For the synthesis of quinoline, you can use anilines that has the nucleophilic site at the nitrogen itself and also at the carbons on the ring at the ortho or para positions. But in order to cyclize to form quinoline, you need to use the ortho positions. So these 2 are nucleophilic sites, and you can use this to react with the 1,3 dicarbonyl compounds. So this carbon attacks here, you use the lone pair of nitrogen attacks here, and if you draw the mechanism correctly, you are going to form the intermediate with 2 OH groups. So these 2 OH groups can be eliminated out by using the proton here and proton here. And after elimination of 2 water, you are going to form 2 new double bonds and complete the aromatic system to form quinolines. Another way to synthesize quinoline is by using the anilines that has amine here, and it also have the aldehydes or ketones at the ortho positions to be the electrophilic site. And then you can use a carbonyl groups. So here is the electrophilic site, and the alpha carbon, because you can form the enolate to be the nucleophilic site. So this nitrogen can attack the carbonyl groups, and this carbonyl compounds can form the enol or enolate. So this carbon can attack this carbonyl group. So you can try to draw the mechanisms by yourself, but eventually you are going to form this new bond and this new bond for the quinoline synthesis. When you draw the mechanisms for heteroaromatic formation, for example this beryllium cation, we know that at this position, since it is the alpha positions to the carbonyl, you can form enol. So this must be nucleophilic site, and these two carbonyl groups must be electrophilic sites, so that you can use this oxygen as a nucleophile to attack. But when you draw mechanisms, there are many possibilities to connect the nucleophile here to this electrophile, and this nucleophile to this electrophile. So if you look at some possibilities for drawing mechanisms, the first way is to tautomerize this ketone into the enol form, so that this carbon becomes nucleophilic. So you can use this carbon to attack the carbonyl group to form the new CC bond. And after that, you can tautomerize back to form enol. And this enol have lone pair at the oxygen. This can be used to attack the carbonyl group here to form the new carbon-carbon bond, the new carbon-oxygen bond. And after that, you can remove the water molecule as a leaving group here as well, and complete the aromatic systems. However, you can use the this enol system that has OH, which is the nucleophile, to attack this ketone as well. So this will form the carbon heteroatoms bond, and after that you can remove the water by using the protons here, and in this case you are going to form the kind of like the enol ether system, which is also nucleophilic that at the carbon positions. This carbon can attack the carbonyl group here and then complete the ring, and eventually you are going to form the beryllium cation as well. So from here you can see that there are many possibilities to draw the mechanisms, as long as you get follows the basic organic chemistry rules, then you should be fine. The underlying message that I would like to emphasize is that the steps in condensation reaction are mostly reversible, but at the end you will get the product nearly always, because it could be that your product is thermodynamically most stable in the reaction equilibrium, or the other possibility is that your product is removed from the equilibrium by a step which is irreversible. What does it mean? So for example, if you have a starting material A, this can undergo the first reaction, reversible reaction with B, and then to C, and then to D. And another way, A can also react to get E, and this one can react to get F. And after that, from F, this can undergo irreversible step to G. For example, the loss of water or something like that. So this step is irreversible. So overall, for the whole reaction equilibrium, eventually the reaction will be driven to the formation of G. Okay, or in the other way, if G is so stable, then this reaction arrow, like the equilibrium, is shifted towards the formation of G, so that the overall scheme is that you are going to form G as a major product. If your product doesn't fall into these categories, then you get the equilibrium that can be adjusted by using Le Chatelier principle. For example, the interrelationship between 1,4-diketones and furans. We know that the synthesis of 5-membered ring heterocycles can be synthesized from 1,4-diketones with nucleophile. In this case, if we remove our molecules of water from 1,4-diketones, you get the formation of furan. And if you add some water to furan with some acidic conditions, you can convert it back to the 1,4-diketones. So this the equilibrium or the major product can be controlled by the amount of water in the reaction. If you have high amounts of water, you get the 1,4-diketones. If you try to remove water out, you get the furan.